Today we're starting a study of hydraulics and pneumatics, which are both a study of fluids. Just a little bit of a different take. So if I have a solid, a liquid, and a gas in the same kind of shape of a container, the solid has molecules that are bonded together. And they're bonded together so rigidly they have difficulty moving, although they do move a little bit. But you have a crystalline structure. When you have a liquid such as water, the molecules are still bonded together, but they're free to move about, which is why you get liquid is able to take the shape of a container, for example. So you still have bonds, but you have freedom of movement. And then finally, when you have a gas, and this is important, the bonds are broken. So the gas molecules immediately take the shape of the container. And there's essentially no bonds. They've been broken. And they're free to move. And this is kind of the key difference between gas and liquids. In fact, they move at a pretty high velocity, usually greater than 1,000 miles per hour. And the faster they go, the more temperature they represent. Now, if we have a piston, and a piston is basically a metal cylinder, and one side of that cylinder is a moving piston. So the piston can move up and down, although it's sealed. So whatever's inside of that cylinder, in this case it's going to be water, is sealed. And we're putting a force on the water with the piston. Well, water, it turns out, is incompressible. When we put that force of the piston on the water is not going to change its shape. Therefore, that force gets spread out to every single water molecule. And that force delivered from the piston is going to reach all sides of the cylinder. If we double the force, we double the force of the piston, we double the force on the sides of the container. So water is incompressible, and we're going to use that feature to develop hydraulics. Gas, on the other hand, is compressible. So I'm just showing 7 molecules of gas. That could be maybe 7 trillion molecules. But when I put a force on the same piston with gas, some of that force is going to have to be used to just compress the gas. So note, I still have 7 molecules, but now they have less space to move about, and they're going to be hitting the walls of that container more often. So that's going to amount to an increase in pressure. But the fact that gas is compressible, this is what's going to be used in pneumatics, which is different than hydraulics, and we'll be doing more of that next class. The emphasis for today's class is going to be the gas laws, and this is what's known in chemistry as PV, so PV equals nRT, N being the number of moles of gas. The number of moles of gas it's just a number. It's like a quantity of gas molecules. So for example, if you have 16 grams of oxygen at standard temperature and pressure, you have Avogadro's number, or you have 6.02 times 10 to the 23rd atoms, which is an unbelievably huge number. That's again at standard temperature and pressure. R is a constant. It's the universal gas constant. And there's actually a number on your engineering sheet, but I'll list it here. It's 8.31 joules per mole degree Kelvin. Now, because it's in Kelvin, we must use Kelvin when we use this equation. PV is powerful as a relational equation. So say I had a fairly large box and I had 3 gas molecules, and then I made that box be smaller, so I decreased the volume. What this says is the pressure is going to go up. The pressure has to go up as long as the temperature is the same. So if the temperature is held the same and the pressure goes up, the volume has to go down. Another way of looking at it is if we hold the volume constant and somehow we light a fire under this one, so we're going to heat up the molecules. They're going to go faster. They're going to get to have a higher temperature. Well, if the volume was the same and the temperature went up, the pressure would also have to go up. That's how we use this as a relational tool. Let's do an actual problem now. And so we have a cylinder and a piston. And so I'm showing like 8 gas molecules. And we're going to say the volume here is 1 liter. Now a liter happens to be 1 times 10 to the negative third, or 1/1000th of a cubic meter. And our initial pressure is going to be 1.5 atmospheres, or 1.5 times 10 to the 5th pascals, or a Newton meter squared. And the initial temperature of this gas, we're going to say, is 20 degrees Celsius. So we want to know how many moles of gas in this cylinder. And so we're going to use the equation that we just talked about, PV equals nRT. So first we need to deal with the temperature, because remember, it needs to be in Kelvin. Right now it's in Celsius. Well, you may remember that absolute zero Kelvin, is negative 273.15 degrees C. And we'll ignore the 0.15 for now. But if we have 20 degrees C, we're just shifted by 273, or 20 degrees C would be 293 degrees Kelvin, which is what we're going to use in solving this. So taking PivNert and solving for N, we get N equals PV over RT. And at this point, it's just going to be kind of plug and chug. So we're going to put in the pressure as 1.5 times 10 to the 5th. We'll use newtons per meter squared here so that we can get the units properly canceling out. The volume is 1.0 times 10 to the negative third meters cubed. So you see we'll have a meter times a newton or a joule in the numerator. And then we just divide by R and the temperature in Kelvin. And the result of all of that is we're going to find N, the number of moles, or N equals 6.61 times 10 to the negative 2 moles. But remember, a mole is a huge number of atoms. So if we take Avogadro's number of 6.02 times 10 to the 23rd, multiply it by 0.01, we'd end up in the range of 10 to the 21 atoms. Huge. So in this problem, we're now going to let some things change. We're going to allow the piston to expand to atmospheric pressure. We want to find the new temperature if the volume expands to 2 liters. So pressure is force over area, which is why we say newtons per meter squared. So in the beginning, we had a force on the piston. The force was causing that relatively high pressure on the gas. And we're now going to remove that force and just allow it to come up so that the only thing holding it down is atmospheric pressure, which is typically listed as 1.0 times 10 to the 5th pascals, or newtons per meter squared. What that basically means is if you're standing on the surface of the Earth, just kind of the weight of that cylinder of gas that's above your head, the weight of the atmosphere pushing on you is the atmospheric pressure. Okay, so solving this problem, we first want to say, okay, P1V1 equals nRT1, applying PivNert to case 1. Well, case 2 is after we've allowed it to expand. And then we would say P2V2 equals NR times T2. Well, the N and the R are the same because we didn't allow any of the gas to escape, and R is just a constant anyways. So if we set NR for 1 equal to NR to 2, and given the fact that they're the same, we end up with P1V1 over T1 equals P2V2 over T2, which is called the ideal gas law. So rearranging this for T2, which is what we're looking for, we can say T2 is basically a multiplier of T1. So it's just T1 times P2 times V2 over P1 times V1. And so we can just plug and chug. When we do, remember that pressure 2 is just atmospheric pressure, which is 1 times 10 to the 5th. We can just say pascals because they're going to, the units are going to cancel. And the original pressure was 1.5 times 10 to the 5th pascals. And similarly with the volume, we can just use liters because the units are going to cancel, numerator to denominator. And so we can just say 2 liters versus 1 liter. And when we do this, we're going to get T2 in Kelvin units because we use 293 Kelvin. So we end up with 391 Kelvin, and then we can change that to Celsius, or 118 degrees Celsius.